on this computer. Why not? All right, so think in your mind's eye for a second about hybridization. Let's make this thing nice and big. So there's kind of stop that. So what's the hybridization in nitrogen and ammonia?
sp3.
And how do you know that?
It has 3 bonds and a lone pair.
So it turns out that it doesn't have to be sp3. And in fact, ammonia can be planar, like that. So it's sp3 when you can think about it as being sp3 when it's pyramidal, and sp2 when it's planar, right? And what are the bond lengths or bond angles in those two cases? Right? You know that the tetrahedral angle is what makes something sp3, I guess, is a way to say it. And you know, the essential issue here is that when you mix an s and 3p orbitals, oh, sorry, you're not looking at my screen. That would be a good place to start. Okay, so now you can see my two examples. All right, so there's pyramidal sp3 and there's planar ammonia, that's sp2. Now, consider those two, which one is more stable? Well, Cheyenne said it's sp3 hybridized, so he's claiming that the pyramidal form is more stable. But in fact, ammonia undergoes interconversion, and nitrogen compounds in general undergo interconversion. They actually invert. So if they were static and you had 3 different substituents on the nitrogen, you could get a chiral amine. But in reality, it goes back and forth between the tetrahedral structure and the planar structure. And in so doing, it can actually scramble its chirality. So let's consider here the various orbitals. So this orbital here and this orbital here are sp3 and sp2 like. Right? But the lone pair in an sp2 thing is really pure p. Sorry, it's sort of a mess, but maybe it's just the wrong size. Let's try and make it bigger. There we go. So this guy here is pure p. So basically, the compound partitions how it uses its orbitals to make bonds. There are 3 of these kind. And it's because there are 3 orbitals that are being used to make them up. There's only one pure p. Okay. All right. So, in fact, these 2 molecules have different basicities. Which one of these geometries is more basic? Any thoughts about that?
Maybe the SP3.
So to answer this thing, you need to know which lone pair is higher in energy. Okay, so 2p orbitals have a higher first ionization energy. Right, that's something that you know already. Right? And why is that? Why is 2p higher than 2s?
Because they interact less with the nucleus.
Yeah, because of nuclear shielding. S penetrates to the nucleus. Okay, so because S penetrates to the nucleus, electrons that are in an S orbital are lower in energy. Right? So ionization energy goes pure P is greater than sp3 is greater than sp2 is greater than sp is greater than S. Okay. So now let's ask this again. The basicity of ammonia in these two different geometries is not the same. Okay, and the question is, which electron pair is higher in energy? Which lone pair is higher in energy? So I just told you the ionization energy goes P is greater than S. And when you mix in S and P together, it changes the energy. So a pure P orbital is higher in energy than an sp3 orbital. Sorry about that. Okay. So in terms of the action of ammonia as a protic base, the compound on the right is more basic than the compound on the left, because the compound on the right, the planar ammonia, has its electron pair in a pure p orbital. Okay. The compound on the right would be more easily ionized than the compound on the left. Easier to pull an electron off the thing on the right. And that kind of makes sense. Just sort of like forgetting all this orbital partitioning and effective nuclear charge stuff for a second. If you're taking a stable structure, this pyramidal one, and you're contorting it and making it planar, you're going to raise it in energy. And so you might expect it, it's going to give up its electrons more easily. The reasoning here is that the partitioning of the orbitals P and S impact the energy of the electron pairs. Okay, so now there's this thing called Bent's rule. And Bent's rule basically says that atomic S orbital character tends to concentrate in lone pairs. Okay. And atomic p orbital character concentrates in bonds, especially, I'll just say in bonds to electronegative elements. Okay, so that's how Bent's rule is written out. The first part, I think, can be understood. Concentrating electrons in s orbitals drops them in energy because s orbitals penetrate to the nucleus better, and that stabilizes that lone pair of electrons. Okay, so that's one simple depiction of this thing. What about the second part? The p orbital character piece concentrates in bonds to electronegative elements. Why does that happen? Well,
Is there less
the way to
charge to
say
stabilize?
this is that p orbitals are more easily ionized. Okay. Another corollary of the same thing is that s orbitals concentrate in bonds to electropositive elements. And why is that? Because the nucleus of the atom that's using its s orbital can better stabilize the electron pair. It's almost like it becomes more electronegative if it uses an s orbital. So it concentrates an s orbital in a bond to an electropositive element because it's a better arrangement of charge in the molecule. Okay, so what is the real hybridization in planar or in pyramidal ammonia? It's not actually sp3. And in fact, there's going to be some hybridization of greater than sp3 so that the lone pair in ammonia can have greater s character. Okay, and this tends to lead, this influences the geometry. All right, so let's take a look at some examples of that.
Sorry, but didn't you just say that it can be sp2 where the lone pair would be in a p orbital? So how do you get
Let's
both?
take this guy here. Compared to these guys here. So it turns out that this angle is close to 90 degrees. This angle here is 101. Okay. So if this angle here is close to 90 degrees, what does that say about the hybridization in this compound? An angle close to 90 degrees here implies that the phosphorus is using p orbitals in making bonds to fluorine, right? So the fact that the angle is so sharp here is a consequence of Bent's rule. It also says that this lone pair up here is almost pure P, or is almost pure S. Let's see here. Whereas on this other side over here, this lone pair has a greater amount of p orbital character in it because this angle is wider. And I'll say lone pair okay. All right. Where are my other notes on this topic? Oh, there they are. Sorry, this guy got put away in the wrong table. All right, so if you have you look at the halogens, and thionyl, fluoride, chloride, and bromide, you get really well-defined trends here. 97.8 for PF3. 100.3, 101, and then these guys here, this is going to be the, well, maybe I'll just change this to E. So this angle here is 92.3, 96.2, and 98.2. Okay. So the angle here, this XPX or F sulfur fluorine or bromine sulfur bromine angle, this tells you about the hybridization of the compound. And you get closer to 90 degrees when you have more electronegative substituents. Okay. I should have written this out here. All right. Now let's do another example. This time, we're not going to change the substituents, we're going to change the central atom. Okay. So before I start writing out the numbers here, take a moment to guess what's going to happen. Okay. We're interested in this angle again. And what do you think is going to happen to that angle as you descend the period? Well, what's the key question to define to answer this thing? What is it that we really want to know about? We want to know about the partitioning of S and P, right? What dictates whether or not oxygen, sulfur, or selenium use an s orbital or a p orbital to make bonds to hydrogen? The relative energy between the two of them is what matters, right? The molecule achieves a better energetic situation by putting lone pairs in s orbitals and using p orbitals, especially when bonding to electronegative substituents, right? The atom is taking electrons away or sometimes donating too. Here, we're not changing the substituents, we're changing the central atom. So we're interested in how S and P change in energy as you go from oxygen and sulfur to selenium. What is the sp splitting as you go down the period? Anybody know the answer to that? Sorry to put you guys on the spot. You're only only ones here, but what dictates this sp splitting? Nuclear shielding does, right? The question is, how does the Z effective or the effective nuclear charge change as you go from top to bottom? Well, the effective nuclear charge goes up as you go from top to bottom because outer electrons don't shield as well. And so when the effective nuclear charge goes up, the splitting between S and P gets larger. Okay, so the sp splitting becomes more significant and these effects become more significant. It becomes even more crucial that the lone pairs sit in an s orbital than a p orbital as you go down the period. And in fact, elements at the bottom of the main group tend not to hybridize. They don't mix their orbitals well at all because there's such different energies. Okay, so what is that going to do to this angle? Well, it's going to mean the lone pairs are more pure S in character. And it's going to use less s orbital to make its bonds. So the selenium hydrogen bonds are going to be mostly p. And as you go up toward oxygen, s becomes more significant. So this guy is 104.5. This guy is 92.1. And this is 90.6. And actually, I have the tellurium value here, 90.2. Sorry, I have to squeeze one in here. Okay. NCl3, same story, 106.8. That's pretty close to sp3, 100.3, 98.9. $97.2. Okay. All right. So the bonds get closer to 90 as you go down. That's a consequence of the effective nuclear charge going up and the splitting between the S and P levels becoming larger. Molecule is much better off if it puts a lone pair in the S orbital and uses pure P's in making the bonds, especially to electronegative substituents. Okay. So, I'll just say, I mean, this is it. Okay, that's the material I wanted to share with you. And I'll tell you that this is a really very, very useful concept. Things like NMR coupling constants and pKa's are defined by these issues. So if you have, an amine that's more pyramidalized, it's a less basic amine than one that's planar. It's easier to deprotonate an sp2 carbon than an sp3 carbon. It's easier to deprotonate an SPCH than an sp3 one. Alkynes can be deprotonated with, they're strong bases or not very strong acids, but they're much more easily deprotonated than an alkane, for example. Okay, because of orbital partitioning. CH coupling constants are larger when you use s orbitals on carbon. So sp CH couplings are higher than sp3. The s orbital that makes up that bond penetrates to the nucleus, and the electrons in that orbital, they communicate the nuclear spin information of the hydrogen, right? That bonding orbital talks to both nuclei, and the magnitude of the interaction between the two nuclei is dictated by the types of electrons. If it's S in between the two nuclei, the couplings are large. So, you can look at a molecule and think about whether the substituents around it are electronegative or what the geometry of the atom is and predict the coupling constant. It's really quite powerful and very reliable. Okay, so this sp splitting is very important for geometry. It's very important for basicity. It's very important for defining the coupling constant. And things like the main group, at the bottom of the main group series, you'll see this. The bond angles are like pure P. There's another property which we didn't talk about so much, but is a common thing in chemistry called the inert pair effect. So lead and tin often take on 2+ oxidation states. They do that because the two electrons that are left behind, lead and tin are in the carbon column. So you've got 4 valence electrons to begin with. The 2 electrons that are left behind go into a 6s orbital. And that 6s orbital is very low compared to the p's. So it's like those 2 electrons are sitting in a core orbital. It's 6s for lead, it's 5s for tin. But that electron pair sits in something that's core-like. You can make tin 4 plus or tetravalent tin. You can make tetravalent lead, but it's actually much more common to be divalent. And it's because that sp splitting is so large that the s orbitals don't really participate in bonding as much. They just house lone pairs. So this sp splitting, the influence of electronegative substituents on it, you know, that you can predict all kinds of properties of molecules if you're aware of that. On the right, we looked at what happens as the central atom varies from top to bottom and the sp splitting goes up. On the left, we looked at the influence of the electronegativity of the substituent. More electronegative substituents prefer p orbitals because p orbitals are more easily ionized. So the molecule uses phosphorus uses a p orbital to make a bond to fluorine. Down here, it uses more of an s orbital. And that changes the bond angle from something closer to 90 to something that is further from 90. Okay, that's Bent's rule. And it's all over chemistry. There are some, I don't remember if this is in the book or not, but if you look up Bent's rule on the internet, what you'll find is a description of where the substituents go in a VSEPR structure. If you've got an electronegative substituent, does it go axial or equatorial? And that's also just like whether or not the geometry of the bonds supports pure P or S. So it's the same sort of idea. And that issue I'm less interested in you know, it doesn't come up as often as some of these other questions about bond angle and their impact on things like basicity and CH coupling constant. Okay, so you can read hybridization, you can read partitioning of orbitals from the geometry. It's a pretty simple principle. Okay. Any you guys want to ask a question about that while you have me here?
I had a question.
Go ahead, Cheyenne. I, for some reason, didn't hear you. Maybe you just unmuted.
Hello? Oh, can you hear me?
Oh, it's because I don't have my volume turned on. There we go. Go ahead.
Hello?
Now I can hear you, sure.
So nitrogen can go from sp3 to sp2 and then it can invert. But would that mean that as you go down the group, because the S and P energies change, then like phosphor would have a harder time inverting and then arsenic would have an even harder?
That's correct. Phosphorus, in fact, is stable, relatively stable at room temperature to inversion. And it's possible to make chiral phosphines because of that. It's like, you know, to make a chiral molecule, you got to have 4 substituents. In a phosphine, the lone pair acts like a substituent because it doesn't invert. Nitrogen pops all over the place and you can scramble. But when the thing is forced to be pyramidal and doesn't invert, it's possible to actually separate R from S and put it in a bottle.
Okay.
You understand what I'm saying when I say R from S? Yeah.
Yeah.
If you have 3 different substituents on phosphorus, that's chiral because it sits still. If it were to invert, then you would invert the chirality. But it doesn't do that because the inversion barrier is high at room temperature. You could also calculate the inversion barrier difference for different substituents. Right? So if you have electronegative substituents, you've got a, you know, you want to put p orbitals down there or you want to orient p orbitals toward the electronegative substituents. And that makes it harder to planarize. So electronegative substituents probably are going to be slower, the phosphorines are going to be slower to invert because the barrier to inversion will be higher. Pretty cool. You know, I mean, it's just such a simple concept and you can predict all kinds of stuff like that.
Thank you.
Do you have another one? That was a good question.
The only question.
And I have it on tape, so everybody will see. That was a good question. Mary, you good?
Can you hear me?
Yeah,
I'm just wondering because you said we were saying that the p orbitals have a higher ionization energy than s,
yes.
but they're more easily ionized. So I guess why is that the case?
Did I get the convention wrong? Let's see here.
Like you drew out the ordering of the ionization.
So p orbitals are higher in energy than s, and that makes them more easily ionized. Is ionization energy a negative number or a positive number? I think it's negative. It's negative. So anyway, P is above S. It's closer to vacuum. Okay. And it penetrates, and that's because of the way it talks to the nucleus. An S orbital has maximum amplitude at the nucleus. A P orbital has a node at the nucleus. So an S orbital feels the nuclear charge more, and the electrons are bound more tightly to S than they are when they're in a P orbital.
Mhm.
So it's easier to pull an electron out of a P orbital than an S orbital. And that's why fluorine prefers P.
Okay. So
Right.
it's like a lower energy cost.
Yeah, exactly. When you use a P orbital to make a bond to fluorine, you don't pay so much penalty to give up that electron. When you use an S orbital, you have to pay the penalty of the interaction with the nucleus or you pay a greater penalty because the interaction with the nucleus is stronger.
Can you just go over again why the s orbitals concentrate in bonds to electropositive elements?
Well, it's the same principle in reverse, right? So if the substituent is electropositive and it's pushing electron density away from itself and more toward the central atom, then it's better if those electrons go into an orbital that interacts with the nucleus well. So it's a competition between the two, and the question is, who is going to take the electrons? The element that takes the electrons will preferentially use an orbital that accepts them well, compared to a fight with another element where that's electronegative. So it's just a relative thing. Another example that I often use is in carbene land. So when you have CH2, that's a carbene, gas phase carbene. You can also have CF2 or carbon dilithiocarbon, carbon lithium 2. Okay, those are all divalent carbon atoms. And what do you think the bond angle is? FCF versus lithium C lithium. Well, for a fluorine, very electronegative. So carbon preferentially uses p orbitals, and the bond angles will reflect that. They'll be closer to 90. Lithium carbon lithium is something that's been computed, and it's basically linear. So it's basically linear.
And the p orbitals orient like 90 degrees just because of like the px, py,
Yeah,
pz.
p orbitals are 90 degrees
Right.
from each other. That's the nature of the p orbital.
Yeah.
So if you're going to use it to make a bond, then the things that are directed at it are also going to have that same angle.
Mhm.
What's the hybridization of carbon in this dilithiocarbene? It's linear. If it's linear, it's like an alkyne, right? Alkynes are linear. So it's an sp hybridized carbon. And the lithium carbon bonds have a lot of S character in it. There are two other pure p orbitals in that molecule, and they house the other two electrons, because dilithiocarbene has two unused electrons. They sit into pure p orbitals.
Even though in other contexts we say that we want to concentrate like lone pair electrons in S. In this case,
Right.
it's better for the energy like stabilization.
Right, because lithium is electropositive,
Yeah.
right? So you're forcing electrons into the thing. And so it takes this linear geometry to put the, you can think about it as like divalent carbon 2 minus with 2 lithium pluses. And so the lone pairs are the
Right,
dynamic
right.
parts, right? And so
Yeah.
there's s orbital character there. Difluorocarbene is 90 degrees or almost, and the 2 valence electrons on the carbon sit in an orbital that's mostly s. And then there's another one, a pure p, that's totally unused. So in dilithiocarbene, you have 2 p orbitals that are half filled, and the ground state electron configuration, according to Hund's rule, is a triplet. And in difluorocarbene, because it's 90 degrees and the electron pair is almost in a pure S, Hund's rule doesn't work. The pairing energy is too large, and so it's a singlet. You'd have to draw that out to maybe to understand that, but you're just considering the 2 remaining orbitals not used in forming bonds. CF2 uses 2 pure P's to make CF bonds and leaves behind 1 S and 1 P. Dilithium carbon uses 2 sp orbitals to make bonds, and it has 2 pure P's left over. And that's where the remaining valence electrons end up.
Can you just repeat which one would be the triplet and the singlet?
The triplet and the singlet has to do with the energy splitting of the remaining orbitals. In CF2, you've got an S and a P, large splitting. In dilithium carbene, you have 2 pure P's, no splitting, right? So there you're going to get unpaired electrons. And in the other case, to get unpaired electrons, you got to have 1 unpaired in S and 1 unpaired in P. And that is, you have to promote the electron. In fact, the pairing energy that you pay is smaller than the energy splitting between the S and the P orbitals. So it prefers to go anti-parallel and put both electrons down in that S orbital instead. So difluorocarbene is a singlet, dilithiocarbene is a triplet. Okay,
Makes sense. Yeah.
yeah, amazing. Just with little Hund's rule, you could predict all that stuff.
Mhm.
You might ask whether you're more likely to get triplets as you go down. What happens when you go down?
Lone pairs have greater S character.
Yeah, because the splitting between S and P gets even larger.
Uh-huh.
Much more likely to get singlets as you go down.
Right.
For lead, it's a no-brainer. Lead is often divalent. You get a lone pair. So those electrons just go into the 6s. And that's why you often have, if you have unpaired electrons, all hell breaks loose. You start making and breaking bonds left and right. But when they're paired and in a lone pair, that's not the case anymore. So it's very common to have divalent tin and lead.
Cool.
Okay. All right. Well,